Anyway, maybe we should begin at this point, and I think we're recording, although the preamble will likely be edited out. Welcome to everybody to, I think it's the last but one of the physics colloquia, and they're thrilled to have as our speaker today Professor Takaaki Kajita from the University of Tokyo, where he is the director of the Institute for Cosmic Ray Research, and he is going to tell us about an exciting experiment, a successor to earlier experiments that have been famously successful, called Hyper-Kamiokande. This, as I believe, he's going to tell us about this, but I believe has got the final go-ahead from the Japanese government in 2000, and it is a large international collaboration with 19 countries involved and growing rapidly, and it is going to tell us a lot about neutrinos. Professor Kajita was got his PhD in the University of Tokyo and worked under Professor Kashiba, who got the Kamioka experiment started and famously discovered neutrinos from the Hun. And then I think in 1998, Super-Kamiokande discovered detected neutrino oscillations and implicitly masses we'll hear more about. And for this research, Professor Kajita shared the Nobel Prize in 2015 with Art McDonald. Today he is going to tell us about the physics and the status and also the timeline of this very exciting experiment. And so I will hand over to Professor Kajita. And I think the best way to handle questions is probably through the chat during the talk, and I'll try and monitor this. And then at the end, perhaps by raising hands in the way which we've all become accustomed to do at the end of the talk. Is that all right to you, Professor Kajita?
Yes, fine. Okay, thank you.
Well, thank you very much indeed, and looking forward very much to your presentation, and I suggest you share your screen.
Okay, well, thank you very much. Well, thank you very much for the invitation to this colloquium. So now I'd like to share my slide. Okay. I hope you see this slide. Okay.
I will do.
Yeah, thank you. Today, excuse me. Today, I'd like to discuss the Hyper-Kamiokande project. This is the outline of this talk. First, I have a brief introduction on the neutrinos. Then I'll briefly discuss the Hyper-Kamiokande project. After this, I want to talk about the physics with the Hyper-Kamiokande detector. First is the neutrino oscillation studies with the JPAC beam. Also, I want to discuss the neutrino oscillation studies with atmospheric and solar neutrinos. Hyper-Kamiokande is primarily the neutrino detector, but we have another physics topics. One is the proton decay, and also we'd like to observe supernova neutrinos. Therefore, I'm going to talk about these topics briefly. Then I will discuss the status of Hyper-K and summarize this talk. Okay, introduction. Well, slightly more than 20 years ago, neutrino oscillations were discovered. In the left side, I show a plot from Super-Kamiokande. Super-Kamiokande observed atmospheric neutrinos, and they found that the neutrino event rate depends on the neutrino arrival direction. Here, cosine Zin's angle is plotted. So 1 means downgoing neutrinos, -1 means upward-going neutrinos. And these black dots show the data, and these hatched histograms show the Monte Carlo prediction. And you can see for upward-going neutrinos coming from the other side of the Earth, there's essentially a factor of 2 deficit compared with the expectation. And if we include nu-mu-to-nu-tau oscillations, the data can be nicely explained. And therefore, this data gave evidence for nu-mu-to-nu-tau oscillations. Also, there was another discovery of neutrino oscillations. That was the solar neutrino oscillations. And the main player was the snow experiment in Canada. And here I plot the constraints from the solar neutrino measurement on the nu-e flux versus the nu-mu plus nu-tau flux. And there are 4 bands coming from snow and super K. And you can see these 4 bands essentially intersect at a point, and clearly the data indicated non-zero nu-mu and nu-tau flux. And that was the evidence for the flavor change of solar neutrinos. So this discovery opened a window to study the physics beyond the standard model of particle physics. Therefore, the community has been extensively studying neutrino oscillations since then. Well, okay, this is the list of the studies and experiments. First, nu-mu-to-nu-tau oscillations were studied by atmospheric and long baseline experiments. And these experiments essentially constrain delta m to 3 square and theta to 3. Second, there was an extensive study of nu-e to nu-mu plus nu-tau oscillations by the measurement of solar neutrinos and reactor neutrinos, and they constrain delta m1, 2 and theta 1, 2. And finally, the remaining mixing angle, theta 1, 3, was discovered about 10 years ago. The theta 1, 3 was measured by long baseline and reactor experiments. And this is the current global fit result on oscillation parameters. Here is theta, sine square theta 1, 2, delta m 1, 2 square, sine square theta 2, 3, delta m 2, 3 square, sine square theta 1, 3, and delta Cp. So clearly, basic structure for 3 flavor oscillations has been understood. However, well, I think I have to say that we still do not know everything. So this is the agenda for the future neutrino measurements. At present, we do not know if the mass state nu3 is the heaviest or the lightest. But to tell the truth, at present, the data slightly favors this mass ordering. But well, this is only 2 to 3 sigma effect. Therefore, we are not convinced yet. Therefore, we'd like to be convinced if nu3 is the heaviest. Also, since neutrino oscillation experiments can tell us only the neutrino mass square difference, therefore we do not know the absolute neutrino mass. So we want to know the absolute neutrino mass. Furthermore, we'd like to know if there is any structure beyond the three flavor framework. Namely, we'd like to know if there are sterile neutrinos. Also, at this moment, we do not know if the oscillation of neutrinos and oscillation of antineutrinos are identical. And if they are different, this is CP violation. And we think the CP violation in the neutrino sector could be very important related to the baryon asymmetry of the universe. Finally, we do not know if neutrinos are Majorana particles. So, in my opinion, these are the main important future agenda for the neutrino studies. And neutrino experiments can tell about the neutrino mass ordering and CP violation. Therefore, I'm going to talk about these topics later. Okay, now I want to move on to the Hyper-Kamiokande project. Well, first of all, I want to look at the history of the water Cherenkov detectors. In the 1980s, there were Kamiokande and IMB experiments. Kamiokande was located in Japan and IMB was located in the United States. And these experiments observed neutrinos from supernova SN 1987A. Also, these experiments discovered the atmospheric neutrino deficit. In fact, this was later found to be due to neutrino oscillations. And Kamiokande experiment observed solar neutrinos and also confirmed the solar neutrino deficit. And as already discussed, the extensive study of solar neutrino told us that the deficit was due to neutrino oscillations. And because of these important results, Super-Kamiokande experiment was approved, and Super-Kamiokande experiment started in 1996. And Super-Kamiokande discovered atmospheric neutrino oscillations. Also, Super-Kamiokande contributed to the solar neutrino oscillation discovery. And finally, Super-Kamiokande was used for the far detector for the K2K and T2K long baseline neutrino oscillation experiments. And K2K used the KKPS, and T2K uses the JPAC neutrino beam. So clearly, these history tell us the usefulness of the water Cherenkov detectors. Therefore, in my opinion, it is natural to think about the next generation water Cherenkov detector, and that is Hyper-Kamiokande. And here, I want to briefly discuss the main point of the Hyper-Kamiokande detector. It will be 72 meters in height and 68 meters in diameter. And the total and fiducial volumes are 0.26 and 0.19 megatons respectively. And because of this huge mass, we expect many important research topics in neutrino physics and astrophysics. The construction started in 2020, last year. And the experiment will start in 2027, we hope. And I want to briefly discuss the location of the Hyper-Kamiokande experiment. Well, so this is the mountain area in Japan, and here is Super-Kamiokande. Now, Hyper-Kamiokande is going to be constructed here in a different mountain, which is about 8 kilometers south of Super K. And the JPAC neutrino beam center is just in the middle of these two detectors, deep underground. And since we are going to use the off-axis beam technology, therefore both Super K and Hyper K are exposed to the same 2.5 degree off-axis neutrino beam. Therefore, we can carry out the neutrino oscillation experiment with the JPAC neutrino beam. And finally, I think I have to mention that the rock overburden is 600 meters, which is shallower compared with the present Super K, which is 1,000 meters deep. Anyway, even with this depth, we think we can carry out various physics. About the technology development for the Hyper K, I just want to tell you one example. This is the photomultiplier R&D result. In the last 10, 20 years, the Hyper K group has tried to improve the performance of the photomultiplier tube. And here I show the photon detection efficiency relative to the present Super K photomultiplier tube. And with the improvement of the quantum efficiency and the photon detection efficiency, the combined total photon detection efficiency is improved by a factor of 2 compared with the present Super K photomultiplier tube. Furthermore, here I show the timing resolution for a single photoelectron pulse. And you can see in the newly developed Hyper K photomultiplier tube, the timing resolution was improved almost a factor of 2. And here is the charge resolution for single photoelectron pulse. And you can see now the single photoelectron pulse is much sharper compared with the present Super K phototube. So in summary, we have many improvements of factor of 2. And furthermore, I want to tell you that the pressure tolerance of the new phototube is improved by factor of 2. And the new tube can survive with the depth of 100 meter water. So we think we have, with this newly developed photomultiplier tube, we can certainly improve the physics performance. Now, I want to discuss the neutrino oscillation studies with the JPAC neutrino beam. Well, I mentioned that Hyper K will be much larger than present Super K. And furthermore, we are going to improve the beam intensity of the JPAC neutrino beam. At present, the JPAC neutrino beam is 0.5 megawatt, but it's going to be improved to 1.3 megawatt. Therefore, in total, the neutrino event rate will be improved by approximately a factor of 22 compared with the present T2K experiment. So this is a big improvement. And this is the JPAC neutrino beam upgrade plan. Well, we are now here, and from now on, we are going to improve the intensities step by step. And as I said, by 2028, the beam intensity will be 1.3 megawatt. And related to this activity, I want to mention the KEK project implementation plan review result. And project implementation plan review concluded that JPAC upgrade for Hyper-K is the highest priority. So this is the highest priority project for KEK. Now, I want to talk about the expected signals. Here is the expected signal for 2.5 years of operation of the neutrino beam. Then, due to nu mu to nu e oscillations, we expect the electron neutrino appearance, and this appearance depends on the CP phase delta. Also, this is the expectation for 7.5 years of the anti-neutrino operation. Again, we expect the anti-neutrino electron neutrino appearance, and again, the appearance depends on the CP phase delta. But the appearance is different for neutrinos and anti-neutrinos. Therefore, by combining the neutrino results and anti-neutrino results, we get the information on the CP violation. And this is the approximate signal and the backgrounds for this experiment. We expect about 2,300 nu mu to nu e signal events. On the other hand, we expect these much background events. In fact, this is the anti-neutrino appearance. And you can see the signal is slightly lower, only 1,600. On the other hand, we expect larger background events for the anti-neutrino mode. Therefore, in my opinion, we have to carry out various detailed studies with the anti-neutrino beam in order to fully understand the background contamination. And well, this is essentially the same plot as before. Here, the event number difference as compared with the CP delta 0 is plotted as a function of the assumed CP delta, delta 90 degree, minus 90 degree, and 180 degrees. So depending on the delta, we expect this much difference for neutrino mode and anti-neutrino mode. And therefore, by using this data, we can estimate the sensitivity to discover the CP violation in the neutrino sector. So this is the expectation after 10 years of operation of the JPAC, neutrino beam, and Hyper-K. And well, of course, the sensitivity depends on the assumed CP delta, but say, if we are most lucky, then we could observe the H sigma effect, CP vibration effect. And of course, we know that there are other large-scale experiments. That is the DUNE project in United States. And I would like to compare the sensitivities from these two experiments. Let's assume 10 years of exposure. So please compare the red curve from DUNE and this red curve from Hyper-K. So clearly, both experiments will have a very high sensitivity around H sigma effect if CP delta is in the most favorable value. Now, so you see there are two projects going on with a quite similar sensitivity. And people sometimes ask us, do we really need two experiments? And my answer is yes. Well, here I show the comparison of the DUNE and Hyper-K projects. Well, the baseline length is quite different. DUNE's baseline is 1,300 kilometers, which is a very long baseline. And due to this long baseline, DUNE have a large matter effect, which is good to determine the mass ordering. On the other hand, Hyper-K will have only 300 kilometer baseline. Therefore, the matter effect is much smaller. And therefore, Hyper-K is not the optimal experiment to determine the mass ordering. But if we want to determine the CP phase delta value, it will be an advantage because we expect smaller effect of matter density uncertainty. And also the beam energy is different. DUNE is going to use the multi-GeV beam and the Hyper-K is going to use sub-GeV beam. And finally, the detector technology is quite different. DUNE is liquid argon TPC and Hyper-K is water Cherenkov. So clearly, these two experiments are complementarity, have a complementarity. Therefore, we'd like to be convinced with the CP violation by the consistent result from these two experiments with very different systematics. And we hope that these two experiments will carry out the experiments in a similar timeline. Okay, now I'd like to move on to the second topic, that is the neutrino oscillation studies with atomic and solar neutrinos. Well, here I show the oscillation probabilities for normal mass ordering. Upper panels are nu mu to nu mu, and lower one is nu mu to nu e. And due to the matter effect, we expect a large resonance effect around 5 GeV for upward going neutrinos. And for neutrinos, if the mass ordering is normal. But if the inverted case, mass ordering case, this large matter effect is for antineutrinos. And by using this effect, we can say something about the mass ordering. And this is the sensitivity of the mass ordering determination based on the atomic neutrino study only. And well, actually the sensitivity depends very much on the assumed sine squared theta to 3. But well, I would say if sine squared theta to 3 is 0.5 or larger, then atomic neutrinos can tell us the mass ordering at about 3 sigma or beta. Of course, we can combine the atomic and long baseline results for the mass ordering determination. And here's the sensitivity. Again, the sensitivity depends very much on the assumed theta 2, 3 value. But if we combine these two data, then after say 5, 6 years, we'll be able to determine the mass ordering better than 3 sigma. And if the theta 2, 3 value is big, then we could determine the mass ordering with more than 5 sigma after 10 years of operation. Now, this is the last slide related to the atmospheric neutrinos. And since oscillation is nu mu to nu tau, it's natural to expect the tau appearance signal in the Super-Kamiokande atmospheric neutrino sample. In fact, it was not easy to select the tau neutrinos. And after many years of studies, we finally published our tau result. And here's the plot. And the gray band is the tau contribution. So at this moment, we have the tau appearance signal at 4.6 sigma level. And in fact, the data is slightly larger than expectation. And due to this, we get, in fact, this 4.6 sigma result. Now, in Hyper-K, I think the statistical significance is no more an issue. The normalization of the charged current cross-section relative to the charged current numeric cross-section can be constrained to about 7% with a 5.6 megaton-year exposure of Hyper-K. And this measurement will help understand the charged current cross-section near the threshold, and which is rather poorly known. And this is the expectation of the determination of the charged current cross-section after 5.6 megaton-year exposure. Well, only unfortunate thing is this is after 30 years of the exposure. Now, I'd like to move on to the solar neutrino oscillations and day-night effect. And well, this is the well-known plot, constraints from the Kamioka experiment and the solar neutrino experiment. And delta M square, preferred delta M square from Kamioka and solar neutrino experiments are slightly different. And delta M square can be independently checked by looking at the day-night effect. By the way, day-night effect is the matter effect due to the Earth matter. And therefore, we expect slightly larger flux during the daytime. And the day-night effect depends on the assumed delta M square. And well, this is the Super-K day-night result. And Super-K day-night result slightly favors the delta M square from the solar global fit. Well, but of course, at this moment, we cannot tell which delta M square is more preferable. Now, of course, in Hyper-K, we can continue the day-night studies. And this is the expected day-night asymmetry sensitivity. And if Kamioka delta M square best fit is the true delta M square, then the day-night effect is smaller. Therefore, even after 10 years of operation, our day-night asymmetry will be a 4 sigma effect. But if the solar delta M square is the real solution, then we expect a larger day-night effect. Therefore, the sensitivity to the day-night effect is larger, is H sigma. So we can clearly get some independent hint about the delta M square from the day-night effect. I think I spent too much time. so I have to hurry up a little bit. Now, I want to briefly discuss the other physics, supernova neutrinos. Well, in 1987, Kamiokande IMB and Batson experiments observed supernova neutrino bursts, but the total number of events was only 24. Now, let's assume a supernova explosion at the center of the Milky Way galaxy. Then we expect to observe 50 to 80,000 events. And this is the expected time profile of the signal. And from this, we can tell the dynamics of this supernova central engine, the explosion mechanism, and also we have the about 1 degree pointing for the supernova alert for multi-messenger studies. So clearly, it will be interesting, extremely interesting to observe the next supernova burst. Furthermore, we'd like to observe the relic supernova neutrinos. We think that neutrinos that were produced by past supernovae should be observed. This will tell us the history of the supernova explosions in the universe. And at this moment, Super SKGD and Juno is about to start the observation. So I hope they will discover the relic supernova neutrinos. But in any case, the number of events they can observe is limited. Therefore, we would like to continue the studies of relic supernova neutrinos with Hyper-K. And well, certainly Hyper-K will measure a lot of neutrinos. And with this high statistics, Hyper-K will measure the spectrum and therefore will tell us the combined information about the history and average behavior of supernovae. Now, proton decays. Well, let me briefly discuss the motivation. It's clear that proton decay is very important for understanding of physics at very high energy scale, granular unified scale. Neutrino mass and mixings and proton decays might be related to the physics at very high energy scale. And I think we are in an extremely interesting era. New large neutrino detectors, Juno, Dune, and Hyper-K will begin the operation in the near future. And these detectors are also very good proton decay detectors. Therefore, I think we should not forget the proton decay searches in the next generation neutrino experiments. And this is the sensitivity. If we assume proton decays to E plus pi 0, then the 3 sigma discovery sensitivity is shown here. And after, say, 20 years of operation, Hyper-K can discover this decay mode if the lifetime is shorter than 10 to 35 years. This is the another decay mode, proton going to neutrino plus K plus. Then I think the Juno will have the best chance to discover them. And here I'd like to discuss the signal and background for the proton decay search. We assume proton decays to E plus and pi 0. And here is the total invariant mass and total momentum plot for the Monte Carlo simulated proton decays. And you can see if free proton decay due to hydrogen in H2O, then the total momentum is typically less than 100 MeV. reconstructed momentum is less than 100 MeV. On the other hand, if a proton decays in oxygen, then due to the Fermi motion, the typical total momentum is, say, less than 250 MeV. Now, this is the expected background, and you can see if we set the 100 MeV cut, we do not have so much background, but if we have 250 MeV cut, then there should be a non-negligible background. So from this, I would say that in order to reach 10 to 35 years, free proton decay from hydrogen is very important. And in fact, this is the expected signal. Well, with the cut total momentum less than 100 MeV, then the expected background is only this much, and we expect this signal. By the way, here we assume that the true proton lifetime is 1.7 times 10 to 34 years, which was the previous super K limit. Now super K has improved the limit to 2.4 times 10 to 34 years. Therefore, I have to say this signal expectation is a little bit too optimistic. Now I want to move on to the status and timeline of Hyper-K. As I said, the construction has already started last year. And now the tunnel construction will be carried out in this fiscal year, and the phototube production has already started, and various other elements will be constructed later. And at the same time, JPAC beam power will be upgraded, and near detector facility will be improved, and we hope to start the experiment sometime in the Japanese fiscal year 2027. And here I show some photos related to the Hyper-K construction. First of all, in the last year, we had a detailed geological survey at really the Hyper-Kamiokande site. Well, of course, these two photos may not mean much to you, but anyway, we do have a very detailed rock survey at the site. Also, now the new photomultiplier tubes were delivered. Some of them are delivered to the Kamioka site. And this is the construction status. Well, here is the entrance, and here is the Hyper-Kamiokande. So first, we have to excavate the access tunnel. And this is the status of the preparation of the entrance yard. And this photo was taken in April 20 this year. And here will be the tunnel entrance. And here's the wastewater treatment facility. By the way, in this site, there is a public road. And people realized that this public road will badly interfere with the excavation activity. Therefore, we decided to slightly change the road. So this is the newly made temporary public road and bridge. And finally, this is really the news. The excavation of the access tunnel started on May 6th this year, and this photo was taken on May 10th. So the excavation started. And this is the collaboration status. We have about 450 collaborators at this moment from 19 countries. And this is the history of the number of collaborators. And you can see there was a big jump of the number of collaborators in 2020 after the approval of the Hyper-Kamiokande project in Japan. And also I'd like to mention, well, certainly in Japan, we have more than 100 collaborators, but compared with the total number of collaborators, Japanese people are only slightly less than, well, maybe about just 1/4 of the total collaboration. Okay, let me summarize. Hyper-K is a next generation multipurpose neutrino experiment. CP violation is the neutrino beam, solar atom-seq and supernova neutrino studies. And also, we should not forget the search for proton decays. And Hyper-Kamiokande is in the construction phase. We'd like to work together with the colleagues from all over the world. And we expect to start the experiment in 2027. Okay, that's all.
Okay, well, thank you very much indeed for a wonderful talk, Professor Kajita. And you've combined the physics, the astrophysics, and the cosmology reach of this wonderful experiment. And you have also told us about the history, the scientific ambition for this project, and its relationship to the many other experiments that are going on. And for that, I thank you for such a wonderful talk. And congratulate you on your progress on being able to start the access tunnel, which is a very exciting development. Perhaps I could start with the first question. Let us look forward to, say, 10 years' time, and you produce an increasingly precise measurement of delta CP, and you find that it is 0. How surprised will you and your theoretical colleagues be by that?
Aha, very good question. Well, well, okay. I would say certainly finding delta CP equals 0 is a kind of disappointing result. But on the other hand, if we can tell that delta CP 0 effect is observed, that would be still wonderful.
Okay, thank you. Giorgio, you have your hand up, I think.
Yeah, sorry, I didn't know what the etiquette was, so I forgot what you said at the beginning. Maybe I can ask. Actually, I'm also cheating because I have 2 questions. One is very well, I mean, it's a very clear one. The other one is more open-ended. The first question is, you mentioned the Dune program compared to Super K, but what about Juno, the same physics, that is the physics of oscillation, and in particular, the hierarchy problem and Juno, and how those things compare? And then the other question, which is more open-ended, is actually from the detector point of view. You know, on the one hand, talk about water Cherenkov, right? There's this evolution from kiloton to 100 kiloton, eventually of Hyper-K, with low threshold, you know, MEV threshold. On the other end, there is Ice Cube, which is 10 to the 9 tons, but it's you know, multi-TeV threshold. And the question is, how do you see those 2 things come together? Can water Cherenkov underground grow even larger? And I was interested in your view in general about this.
Okay, thank you. Well, certainly, first of all, as far as the mass ordering is concerned, I really hope that Juno will have a clear data on the mass ordering. Well, since Juno is going to start rather soon, I really hope that they'll tell the mass ordering. And in fact, that is good to us because, well, to be honest, Hyper-K is not a good machine to measure the mass ordering. Some other input from outside will be most welcome. About the relation between ice cube and Hyper-K, well, certainly, I think we definitely need these two facilities. Super-K, Hyper-K is in the MEB to GeV range, and ice cube is in the higher energy range. And definitely by combining these two, we get the most on the physics.
So perhaps I could ask a follow-on upon that. You displayed the schedule for Hyper-K. What is the corresponding schedule for Juno?
Oh, thank you. Well, if we look at the official schedule that was presented some years ago, they told us that they will start the experiment in 2026 or so, but I do not know the present schedule of Dune.
We have another question from Tommy Wen-Chin.
Thank you for the wonderful talk, Dr. Kajita. I'm an undergrad and I don't have much background in neutrino oscillations, but then I was wondering at the beginning, at the first few slides, there was one where you showed how the signal of the anti-neutrino is a lot weaker than the neutrino. And you mentioned about how in your opinion, you should improve upon that measurement. And I was wondering why that is. Why is the anti-neutrino weaker than the neutrino?
Oh, okay. Thank you very much for this question. And I'm sorry, I didn't tell the reason for this. First of all, the anti-neutrino cross-section is smaller than the neutrino cross-section by approximately a factor of 3. Furthermore, since the anti-neutrino beam is produced by pi minus decay, while the neutrino beam is produced by pi plus decay, on the other hand, when we produce the pions, we have more pi plus than pi minus. Therefore, by combining the neutrino flux and the neutrino cross-section, we expect smaller anti-neutrino signal.
That makes sense. Thank you.
Do we have more questions? Perhaps I could ask another off-the-wall question, because it's one that I am often asked, and you will probably have a better answer than the one that I can give. What are the prospects of measuring cosmological neutrinos with very, very low energies from the Big Bang? What are the prospects, and what is the least unpromising way of doing that?
Well, thank you very much for this question. Well, to be honest, I have no idea, and I do not know if anyone has any convincing idea to observe them. I think it would be most welcome if we have any idea to observe them. So
the undergraduates who are listening to this lecture, that is your homework problem. Jeff Scargill, you have your hand up.
Yes, thanks. You showed a picture, I guess, of the expected light curve in neutrinos from a hypothetical supernova at the center of our galaxy, I think. Slide 27, if I have it right. Near the peak of the luminosity, there was some distinct oscillations What's the mechanism of producing those oscillations?
Yeah, well, thank you very much. That is Sashi, that is the, well, I forgot what was the, some kind of instability. Matter moves very rapidly. So we could see this kind of dynamics during the supernova explosion by looking at the neutrino profile.
I see. So if you observe that, it would confirm that the model was working right, I guess. Is that the idea? Thank you.
So I think we're now at the hour, and so I want to finish by once again thanking Professor Kajita for a wonderful, clear and talk about a very exciting project, and we look forward to the results when they come, starting in 2027. So let us give a virtual round of applause to Professor Kajita.
Thank you.
Thank you very much.